While you're more than welcome to glance at the key features and innovations of YOLO12 on the Ultralytics site, we'll instead go straight to the source and briefly walk through the official paper. As mentioned earlier, these innovations were introduced by Yunjie Tian, Qiqiang Ye, and David Dorman. In this section, I'll focus primarily on the architectural changes, so we can later explore how they're implemented in code. YOLO12 builds on the attention mechanism introduced in YOLO11, extending it to more blocks and adding further improvements. Here, you can see a comparison between different YOLO versions and real-time detection transformers. YOLO models traditionally rely more on convolutional operations, while RT deters are grounded in attention mechanisms. Although that distinction is becoming less clear, and YOLO12 is a prime example of that shift. The performance curves shown for YOLO12 likely assume the use of flash attention, which may not be available on all hardware. More on that shortly. Since the performance differences across models are quite small, it's worth testing different architectures on your dataset and use case to determine which one performs best. Some of the innovations stem from identifying inefficiencies in attention-based mechanisms compared to more traditional CNN-based approaches. For example, they highlight the quadratic computational complexity and inefficient memory access patterns in standard attention modules. To address these challenges, the authors propose three major improvements. The area attention module, which splits the attention's query, key, and value tensors into separate spatial areas, reducing complexity and improving locality. The residual efficient layer aggregation network that enhances feature aggregation through residual connections and scaling. This structure forms the new A2C2F block. Not all model sizes use this component, only the large and extra large variants include it, as well as architectural refinements such as removing or replacing blocks like SPPF and C2PSA, as we saw earlier. Lastly, there's a configurable MLP ratio parameter, which affects the dimensionality inside the feed-forward layers. It's tunable and typically varies with model size. The default is 2, which is also what we'll use for our nano model. When it comes to related work, it's no surprise that YOLO12 builds upon previous YOLO versions. For example, YOLOv12 introduced the cross-stage partial CSP network, which, as we saw earlier, helps aggregate features from the backbone into the neck. By the way, if you're curious about YOLOv12 and how far we've come since, feel free to check out my series covering that algorithm. It also draws heavily from YOLO11, which introduced the C3K2 block, still present in YOLO12. Additionally, the lightweight depthwise separable convolution used in the detection head of YOLO11 has been carried over. Feel free to check out my videos on these topics if you're interested. These evolutions reflect the ongoing contributions of a vibrant computer vision community, continually refining real-time detection models. Additionally, at the bottom here, you can see several attention-based approaches, with this paper introducing the area attention method. I've gone through the code and haven't found a way to switch the area division to vertical. From what I've seen, the current implementation focuses on the left side image, splitting the image into horizontal areas. Again, the paper mentions several attention-based approaches, such as self-attention over local windows, axial self-attention, and crisscross attention, as we saw earlier. It also provides more details about flash attention, which addresses high bandwidth memory bottlenecks that lead to inefficient attention computation. This is achieved through I/O optimization, reducing memory access and improving computational efficiency. The authors use flash attention in their experiments. However, as you'll see later, it requires specific NVIDIA GPUs. If your hardware supports it, you'll benefit from faster attention computations. But everything still works without it. Since I'm using a Mac, we won't be using flash attention in our analysis and visualizations. And down here at the bottom, they introduce a figure showing different architecture blocks with the residual efficient layer aggregation block, one of YOLO12's key innovations, shown all the way to the right. We'll dive deeper into this diagram later and walk through it step by step, but I wanted to briefly highlight it here. The authors identified two main inefficiencies of self-attention. First, the computational complexity. As the number of spatial pixels increases, the cost grows quadratically since each pixel attends to every other pixel. While we'll discuss this in more depth later, let me briefly illustrate the concept using a snippet from YOLO12's attention maps. If you're interested, I also have a full video dedicated to this topic. We'll revisit these calculations and visualizations when analyzing attention in YOLO12 later on. You can see how each token or spatial grid cell assigns importance to all others, regardless of distance. In this example, even though distant pixels don't contribute much to the attention weights, computations are still performed for all of them. As we get closer to the car region, you'll notice that tokens corresponding to the car strongly attend to nearby tokens, as the model learns to focus on semantically related regions in the image. So while attention is highly effective at capturing global dependencies, it also increases the model's computational load and therefore slows it down. What's interesting is that most meaningful interactions tend to occur within a localized region. This leads to the second inefficiency, memory access. Attention's memory patterns are less efficient than those in convolutional networks. These observations motivate the idea behind area attention, which we'll explore more later. The core idea is to divide attention into spatial areas and focus locally, reducing both computation and memory costs while still capturing useful context. Here, the authors provide a thorough comparison with other models in terms of gigaflops, number of neural network parameters, average precision, and inference speed. But for now, let's keep moving. For a visual feature f with dimensions of n by h by d, where n is the number of tokens, h is the number of attention heads, and d is the head size, the computational complexity of self-attention is approximately 2n² hd. We'll take note of this formula for now and revisit it later. As the authors point out, it's no surprise that if we split the input feature map into, say, 4 areas, the computational complexity becomes roughly a fourth of the original. This is due to the reduced number of token interactions within each area. Here, the authors recognize that the attention mechanism introduces additional optimization challenges, particularly in larger models, which can lead to instability and convergence issues. To address this, and drawing inspiration from the ELAN network, top right, which is designed to improve feature aggregation, they propose residual ELAN in the bottom right, which introduces a residual shortcut connecting the input directly to the block's output, scaled by a factor. Additionally, while retaining the one-by-one convolution after the transition layer, they incorporate area block modules, whose outputs are passed both to the next module and to a final concatenation step. It's worth noting that the nano, small, and medium variants of the model use the residual ELAN structure, but do not leverage the residual path or the scaling factor. All of these will become clearer when we later walk through the architecture blocks step by step. As we've already mentioned, 2 modules have been removed in YOLO12, with some of their functions, like attention, now handled by other parts of the architecture. We've also discussed the MLP ratio used in the feed-forward network. And finally, something we haven't touched on yet, the positional encoding. In YOLO11, this uses a separable convolution with a 3x3 kernel. In YOLO12, it still uses a separable convolution, but with a larger 7x7 kernel, allowing for a wider receptive field in positional encoding. We'll take a closer look at these when we dive into the code. The authors conducted a number of experiments and ablation studies to determine the optimal design choices for each model size. While we'll focus primarily on the nano model when exploring the code and visualizations later, we'll make sure to point out whenever the diagrams differ for the large or extra large variants. When it comes to the experimental setup, the main difference compared to YOLO11 is that YOLO12 required 600 epochs, double the typical 300, to converge to an optimal solution on the COCO dataset. As we've mentioned throughout, their baseline is YOLO11, reusing many of the same components, such as the convolutional blocks, the C3K2 modules, and the attention mechanism, although YOLO12 expands upon these. The authors also performed a comparative analysis across different hardware platforms to evaluate performance differences and note that all of the NVIDIA GPUs used are flash attention compatible. Finally, as we saw earlier, they benchmarked YOLO12's results against other state-of-the-art models. Finally, I personally appreciated these diagnostic studies, with results shown below for the nano model, unless otherwise noted. The authors systematically tested individual components, modifying one at a time, to evaluate the impact on average precision and inference speed. On the top left, they confirmed that implementing attention with convolutional layers and batch normalization yielded the best results. To the right, they also experimented with a plain vision transformer, the NA row, and with removing stage 1, a convolutional block, or stage 4, a C3K2 module, but none of these changes led to further improvements. Their best results came from training for 600 epochs. At the top right, they found that a 7x7 window for positional encoding worked best. Although a larger 9x9 window improved precision slightly, it came with a latency cost, so they opted against it. At the bottom left, they confirmed that there's no need to add explicit positional embeddings, as is common in other attention-based architectures. Area attention was preferred and is a core focus of the paper, because although it slightly reduces precision, the speed benefits are substantial. Continuing to the right, they identified an optimal MLP ratio, 1.2 for larger models and 4 for the nano model. And finally, on the far right, flash attention proved to be the best choice, if your hardware supports it. We've already talked about the ablation studies. Feel free to explore the full details if you're curious. The key takeaway is that the authors validated the effectiveness of their design choices, including both residual ELAN and area attention, across different model sizes. In terms of speed, their results show that YOLO12 performs very well, even surpassing other models when using flash attention. Lastly, in the attention visualizations, we can see how the model benefits from area-focused attention, achieving stronger focus on relevant regions and sharper perception of objects and boundaries. And that pretty much brings us to the end. This section is the text explaining the diagnostic studies we already covered. It continues onto the next page too. Since we've been going through the paper top-down, it's not unusual that we saw the figures before the corresponding text, but we've already discussed it. Next, we have the training hyperparameters, which are very similar to YOLO11's. The main difference is the number of epochs required, and that wraps up the paper. At the end, they also mention a caveat regarding flash attention and its hardware requirements, as we already mentioned. So with that, kudos again to the researchers. Now we're ready to take all these innovations and see how they're actually implemented in code. Confident that we haven't missed anything. It's time to solidify the concepts with concrete examples.